Hey everyone, welcome back to ThinkTech. In today's podcast, we'll discuss about containers, a technology that has revolutionized the world of software development and deployment. Containers have become increasingly popular in recent years because they allow developers to create, package, and run applications in a lightweight and portable manner. In this episode, we'll explore the technical details of how containers work, the benefits of using containers, and the most popular containerization technologies such as Docker. We'll also discuss some of the challenges and best practices of using containers in real world production environments. So, whether you are a developer, a system administrator, or just interested in learning about new technologies, the episode is for you. So let's dive into the world of containers and discover how they are changing the way we build and deploy software. Containers are a type of lightweight virtualization technology that allow developers to create, package, and run applications in a portable and isolated environment. Container is nothing but an executable package that includes everything that is required to run an application, such as the code, dependent libraries, system tools, as well as the runtime. Containers use operating system level virtualization to provide an isolated environment that is separate from the host operating system, but without the overhead of traditional virtual machines. This is something that we'll discuss in detail later. But what this means is that multiple containers can run on the same machine, each with their own isolated runtime environment, and they are very lightweight as compared to traditional virtual machines. Containers have become increasingly popular in recent years because they allow developers to create and deploy applications in a consistent and repeatable way, regardless of the target environment, which was very difficult to do before containers came into existence. And they're also highly scalable and very easy to manage. There are a lot of sophisticated orchestration technologies like Kubernetes that allow management and scaling of containers very easy. So that is why containers have become the key technology for building and deploying modern applications in cloud-based environments. So before understanding what containers are, let us understand why do we need containers and what was the reason that container technology was actually developed. So before containers came into existence, the unit of deployment that we had was virtual machines. Now, virtual machine is a great piece of technology that for the very first time allowed virtualization of physical resources. But there are certain limitations with virtual machines. And the biggest one is its size. For anyone who has worked with virtual machines may know that the size of a virtual machine can be in few gigabytes, right? And this became one of the major limitations for deployment or scalability of virtual machines to run more and more applications. The reason or the primary reason why virtual machines are very heavyweight is because we have to pack an entire operating system every time we are creating a new virtual machine. This is irrespective of the fact whether the application that is going to run on that VM is heavyweight or not. We have to package an entire operating system before we can ship it out to clients for use, or we can deploy it on the target environment. So this caused a lot of problems with respect to the scalability of virtual machines and the density of virtual machines, which means how many virtual machine can run on a single physical machine, because an entire operating system was packaged with a virtual machine. So obviously the resource requirements for a virtual machine is very, very high when compared to present day containers. And second problem that we faced that was not related to virtual machines is of dependency management. So assume there are two applications that I want to run on my system, application A and application B. Application A requires Python maybe 2.7 and application B requires maybe Python 3. So to have two different Python environments on the same operating system is not practical and very difficult to maintain. So how do we basically run two applications which require different Python versions? So that was very difficult to achieve before containers came into existence. One possible way is to use VMs. You can package application A in a separate VM which has Python 2.7 and application B on a different VM which has Python 3. But again, that is very wasteful because The only requirement that we had was different Python runtimes, and because of that, we have to create two separate bulky virtual machines and run those applications on separate virtual machines. So these were the problems that existed before containerization technologies came into existence. And the reason containers have been so popular is because they have been able to solve these problems in a very efficient manner. So, having talked about why containers were actually needed and what were the problems that we were facing before containers came into existence, let us talk about what do we need to run containers. So, unlike virtual machines, containers do not have operating system of their own. They share the host operating system. Therefore, it is important that we come up with constructs which allow us to run containers in an isolated and a safe manner. So primarily there are three requirements that we need to fulfill to run containers in an isolated and a safe manner. The first one is visibility restriction, what the container is able to see. The second one is resource restriction, what the container is able to use. And the third one is privilege control, what accesses can the container or the users inside the container have as compared to the accesses for users that are outside the container. Now, a lot of tutorials that I have seen or articles that I have read directly talk about the technologies that we use to achieve these key properties while building container technologies, but do not talk about how the evolution of these technologies happened. So it is not like all of these technologies were present at the exact same time and they were just combined to form containers. There was a whole evolution or an iterative process that happened behind the scenes with various different technologies being developed, tested out, and then few shortcomings being removed. And that is how the present day technologies or the containerization technologies that we have today came into existence. So I think to get a bigger picture and to understand these things in depth, it is important that we also talk about those technologies as well. And therefore, in this podcast, we'll cover those topics as well, and we'll not directly jump into how these things are solved today. So the first thing that we'll talk about is change root, CH root. So CH root was one of the first attempt to solve the isolation or the visibility problem. It is basically a Unix command that allows you to change the root directory of a process or a set of processes. This means that you can run a process or a set of processes in an isolated environment that has its own file system root directory. So when you run a process or set of processes in a chroot environment, they can only access files and directories within the chroot directory and its subdirectories. So this allows you to isolate the processes from the rest of the file system, which can be useful for security purposes or for testing purposes, or in our case, to achieve isolation between multiple different containers. So for example, you use a chroot to create an isolated environment for a web server or maybe for a database server. So by running the server in a chroot environment, you can limit the access to the files and directories and prevent the users inside that container from accessing any other part of the file system. This can help prevent security vulnerabilities and makes it easier to manage the server. Chroot is often used in combination with other containerization technologies to provide additional layers of isolation and security for containerized applications. However, chroot is not a complete containerization solution. This was just an attempt at solving one of the key problems because it only provides file system level isolation and does not provide any other type of isolation such as network isolation or process isolation. Another problem with chroot is that it does not differentiate between the root user which is running inside the container when compared to the root user which is running outside of the container. So if a root user is running inside a container, it almost has the same privileges as the root user outside the container. So basically it can break out of that illusion of different root directory and can access contents of the file system that it is not supposed to access. So this again was something that chroot did not take care. And also there was no attempt for resource constraint while building chroot, it only focused on the visibility restriction point of view, and that is why it could not become a full-fledged containerization technology on its own. The next thing that we'll talk about is FreeBSD jail. So FreeBSD is a operating system that is developed and managed by Berkeley. BSD stands for Berkeley Software Distribution. It is a very advanced operating system as compared to Linux, and also a very agile operating system which is very quick to add new features to itself. So FreeBSD came up with a very cool concept of FreeBSD jail. FreeBSD jail is type of a containerization technology that is built into FreeBSD operating systems. And what FreeBSD jail allows you to do is to create an isolated environment within a FreeBSD system. And in that isolated environment, you can run applications as if they were running on their own dedicated servers. So a jail provides a virtualized environment that is separate from the host operating system, similar to the container or a virtual machine. So FreeBSD is actually the front runner to present day containers. This is one of the most successful technologies that ultimately evolved to become the technologies that we use in present day containers. So FreeBSD jail allows you to create multiple isolated environments within a single FreeBSD system, and each of this isolated environment has its own file system, network stack, and process space. So this means that you can run multiple applications on the same server without any interference amongst each other, without worrying about any interference of those applications amongst each other. And again, one of the benefits of using FreeBSD jail is that they are very lightweight and efficient, unlike how we had in our traditional virtual machines, which were very heavyweight and inefficient, because they required a separate guest operating system, which is not the case with FreeBSD jail. They do not require a separate guest operating system. It uses the host operating system's kernel and share the same resources. And this is what makes jail an efficient virtualization technology as compared to previous virtual machines. Another benefit of FreeBSD jail, as we discussed, is that they are highly secure because they do not allow any interference. You do not have to worry about any security breaches that might occur between different processes running amongst different jails. So this again is a very important benefit that FreeBSD was able to bring in, and which translated into present day containerization technologies also. So just to summarize, FreeBSD jail is a containerization technology that allows you to create isolated environments with a FreeBSD system, and it is lightweight, efficient, and a secure virtualization technique. Therefore, is a great option for running multiple applications on a single server, and a lot of the learnings that we had from FreeBSD jail translated into present-day containerization technologies. So now, having talked about the history of different technologies that were tried and tested to solve the three key requirements of building containers, let us talk about what do we have now. So today, to solve the first problem, which is restriction of visibility, which basically means we want to restrict what a particular process is able to see or a particular container is able to see, we have something known as kernel namespaces. So kernel namespaces are a feature of Linux kernel that are used in almost all containerization technologies, very prominently used in Docker, to provide process level isolation. A namespace is a way to isolate a set of system resources such as network interfaces, process IDs, file systems, ports, and many other things. So it appears just like in FreeBSD jail, it appears like a process is running in its own separate environment, in its own separate dedicated server, when it is assigned a particular kernel namespace. So whenever a container is started, a new namespace is created for it, which provides an isolated environment in which that container can successfully run. Each namespace is independent of other namespaces on the system, which ultimately means that the processes running inside a namespace cannot interact with. So to start with, every process is assigned a default namespace, and all the processes in the same namespace have the same view of the file system. And as and when a process is allocated to a separate namespace, then it is not able to see the file system or any other resources that are not present within that particular namespace. So this gives a very strong isolation property that is required to restrict the visibility of processes that run inside the container. So for example, let us take a use case of network namespace. So network namespace are used to create virtual network interfaces that are isolated from the host network interface. They are separate from the host network interface. But what a virtual network interface allows is, it allows the container to have their own IP address, routing table, and network interfaces. So this basically looks like a container is running on the same host system, but it has its own IP address, it has its own routing table. So it looks like it is a complete different entity altogether that is running, with which you can connect independently. Similarly, we have PID namespaces, which allows you to isolate the process ID space. So I think all of us would be aware that we cannot have two processes with the same process ID on the same operating system, because process ID is basically a way for operating system to identify a particular process. However, with kernel namespaces, we can even virtualize process ID namespaces as well. So you can have two containers, two processes inside those containers can have the same PIDs without any conflict or any problems. So this allows the containers to run their own set of processes without interfering with other containers or the host system. So this again gives a very strong isolation guarantee that you don't even have to worry about assigning process IDs that either the host operating system has not assigned or other containers have not assigned. So this runs in complete isolation and oblivious to any knowledge of any other container or any other process running on the host operating system. So overall, kernel namespaces are a very powerful feature that allowed containerization technologies to provide process level isolation and create isolated environments in which application can successfully run. Now coming over to the second requirement, which was of resource constraint or resource restriction. To achieve resource restriction, we use with something called as control groups or C groups. So control groups are again a Linux kernel feature that are used by almost all containerization technologies such as Docker to manage and allocate resources. C groups allow you to control and limit the amount of system resources that a particular container can use, such as the CPU cores, the amount of memory it can use, the port range that it can use, network bandwidth that a container can use, how much disk IO that container can do. So all those granular level controls of resources we can control with the help of C groups. So similar to how namespaces are created, whenever a container is started, a C group is created for that container, and then the C group is used to limit the resources that the container can access. For example, you can use C group to limit the amount of CPU that a container can use, which prevents the container from monopolizing the system resources and affecting other containers or processes. This was again a very big problem or a big use case to solve, that if we are allowing multiple containers to run on the same host operating system, we need to make sure that there is a way to restrict how much resource a particular container can use, so that no malicious container can hijack the entire system and then prevent any other containers to run on that host machine. So C groups were very important development, technological advancement that made successful containerization technologies a reality. C groups can also be used to prioritize resource allocation among containers. For example, we can assign a higher CPU priority to a very critical container. For example, if you have a database running, then that is a very critical container, and you can assign it a more higher CPU priority, so that as compared to any other container, database container is given a priority for running CPU intensive load. All in all, C groups are a very powerful feature, just like kernel namespaces, that allows you to manage and control the resources that are available to the containers. And this again was one of the major advancements that made present day containerization technologies to be successful and possible at the very first place. So we saw that how present day container technologies like Docker use Linux kernel features of namespaces and C groups to create isolation and resource constraint among different containers that are being run on a host operating system. Now, another important point or one other important thing that I would like to talk about with respect to containers is copy on write file system. So a copy on write file system is a type of a file system that uses a technique called copy on write to manage the file system changes. So in COW file system, whenever a file or a directory is modified, instead of overwriting the original data, the file system makes a copy of the data and modifies the copy. So why are we talking about copy on write file systems? What is the importance of copy on write file system for containerization technologies? So actually COW file systems are often used in containerization technologies such as Docker and Kubernetes to efficiently manage container images and file systems. So whenever a container is started, the read-only version of the container image is mounted as the root file system of the container. And as the container writes to its file system, the COW file system make copies of modified files and directories so that the original files in the container image are not modified. So this approach has several benefits. For example, first benefit that comes to mind is that it allows containers to share a common read-only image, which reduces the amount of storage required for each container. So there are obviously scenarios where a same image is used by multiple containers. Now, if we make separate storage of that image for every container that we want to run, that will not be the most optimal utilization of the resources that we have at our disposal. So COW basically allows you to share common image information amongst multiple different containers. Second benefit that we have of copy on write file system is that it allows containers to start quickly, as only the modified files need to be copied to the container file system. Rest of the shared information is obviously at one particular location itself. Another benefit that we have for COW file system is that it allows containers to be rolled back to a previous version by just simply discarding the modified files. So if you discard the files that the containers have touched during that particular run, then you automatically roll back to the last good configuration of those particular containers. So COW file systems are not specific to containers. They can be used in other use cases also, and they are frequently used for snapshotting and backup systems. But this is again an example of how a separately developed technology has helped improve the containerization technologies that we have in place today. Because COW file systems, although they do have some performance overhead, but the benefits that they are able to generate by allowing us to share images amongst multiple different containers is a very important advancement for our present day container technologies. Now we have talked about how containers used to work earlier, what are the technologies that we use today. Now let us talk about few of the challenges that we have with containers. So the very first challenge that we have with containers is that containers use the host operating system. So unlike virtual machines which had their own operating system, even if you wrote some code that generated a kernel panic, only the operating system inside that virtual machine would crash and then the entire virtual machine would crash. But it would not impact any other virtual machine that was running on the same system. However, with containers, since we are using the host operating system or we are sharing the host operating system, if any container writes a code that can trigger a kernel panic, then the entire host operating system would crash, thereby taking all the containers that were running on it down as well. So this is a major problem or a major limitation, I'll say, that we have with containers, because you need to have a certain level of trust amongst all the containers that are running on the host operating system, so that you sort of have trust that no container will actually write a malicious piece of code that can create or trigger a kernel level panic and crash the entire host operating system. And the second challenge that we see with containers is the host operating system compatibility. So with virtual machines, as long as the hypervisor can run the operating system or the architecture on which that operating system is based, you can run multiple different virtual machines on the same hypervisor, same physical machine. But that is not the case with containers. Containers, since they use the host operating system, the container image has to be compatible with the host operating system. For example, you cannot run a Windows container on a Linux operating system, because whatever requirement that container has with respect to Windows operating system will not be present on a Linux operating system, and since there is no operating system inside the container itself, it will not be able to successfully run. Now, there are few other challenges also with containers, such as orchestration, managing scalability, managing resources and storage. But this is not something that have not already been solved or is in the process of being solved by current orchestration technologies. So this is something that we will not discuss, because these problems are not intrinsic to how the containers are designed. But however, one point that I like to mention here is that although the containers have abstracted a lot of hardware interaction that we used to do for code deployment with virtual machines, but there is still some interaction that is needed. For example, scenarios or deciding how to run your container, how do you pull your container, how do you create your container, where can a container run. So all those things, all these infrastructure interactions are still present, and that is why the next advancement or the next evolution of containers is serverless. And we already have a podcast on serverless computing, how it actually works, what are its benefits. So I really suggest you that if you like this podcast, please go over to that podcast as well and understand how serverless computing is the future of software development in cloud infrastructure. And with this, I think we can conclude our discussion about containers. So we covered a lot of ground in this podcast. We discussed what containers are. We understood why do we need containers and what was missing in virtual machines. Then we talked about what do we need to successfully run containers. That is, first point is visibility restriction and second is resource constraint. Then we also understood how the present day technologies of kernel namespaces and C groups came into existence. We understood that these were not a one-time process, but there was a lot of iteration that went into coming up with these technologies. We discussed about chroot, we discussed about FreeBSD jail, and then we talked about how control groups and kernel namespaces work. And in addition to that, we also discussed about how copy on write file systems work and why, although developed independently, they also help improve the efficiency of container technologies that we have today. And then finally, we discussed the challenges with containers, the security challenge that we have, as well as the compatibility challenge that we face with containers. So thank you for listening to this podcast. I hope you found something insightful and interesting in our discussion about containers. Be sure to listen to all our future podcasts. Please follow me on Spotify for getting notifications about such interesting discussions in future. As of now, this is Shivam signing off.